up, we have Emerald Bresnahan. Emerald is a freshman, and she plans to be a physics major. So yesterday we did a quick run through here of all the talks to see how they would go. And immediately after Emerald finished her talk, Ben just, during the feedback phase, raised his hand and said, I just, as a response to that, I just wanted to tell you that you're the single coolest person I've ever met. Emerald was, out of more than 2,000 entries, Emerald was selected as a finalist in YouTube's Space Lab contest. So just a taste, maybe you're starting to get the same sort of excitement that Ben had. So please, everyone, allow your brains to be blown into space, and welcome Emerald.
Last December, I entered YouTube Space Lab, and I entered an experiment to possibly be done on the International Space Station. And long story short, I ended up being one of the top 3, and last week I was in DC with all the other contestants, and we got to know each other, and we some politicians. Yes, politics were part of that too. And yeah, so here's what the YouTube channel looked like, and it's been really great. Go on there and see some of the great experiments and space videos. Really cool. And we also got to go on a zero gravity flight, which was pretty amazing. Here's some pictures from that. All of us floating around up there in what the experiments would possibly be in, the microgravity, 0G, there we all are. And that airplane, it went in parabolas like this, and as we were going down, we were weightless. It got to float around, and water was floating everywhere, and people floated around. Nobody knew where the ceiling was. It was fantastic. And while I was not a global winner, though, the organization who would be sending up the global winners did, called BioServe, did express interest to speak with me further about my project, which is pretty exciting too. So it's not the end for my possibilities. And this summer, the Konotori H-11 transfer vehicle will be taking those experiments up. So that's exciting too. Be on the lookout for that. And my experiment, finally, is that I'd like to grow snowflakes synthetically in the microgravity conditions of space using this vapor diffusion chamber. That's my schematic there. And I altered it for the microgravity conditions of space, and I'll describe it right now for you. There's water chambers up on the top, and because there's no gravity, it's not going to fall down directly through the moist felt right there that collects it. So it would have to be squeezable water reservoirs, so it could be pushed down into the chamber. And the top is, I think there's a laser on here. Oh yeah. On the top would be very hot, and the bottom would be cold. And it'd be supplemented with dry ice, because in the ISS, the International Space Station, there are regulations for certain generators and things like that. So it'd be supplemented with dry ice, and then so that sublimation would have to be taken into account to get enough up there, and that's how dry ice turns into vapor directly. So that has to be taken into account. And there's a tungsten wire leading up to the center of the chamber right here, where a snowflake would grow. And right here, the air would be super saturated, and that means that there's the perfect temperature and amount of water vapor there for a crystal to possibly form. And I'll just grab some snowflake growth for you right now. Here we go. And that's called a morphology diagram. And I think that a zero gravity snowflake would fall somewhere around here if it could be done. And I concluded that the snowflake could be grown in the microgravity conditions of space, then it would grow indefinitely as long as enough materials were available. It would keep growing fractals outward, and since it wouldn't fall or wouldn't be blown around or someone would eat it or turn it into a snowman, it would grow very big as long as the chamber was big enough to allow, and that it would have a unique formation outside its hexagonal base. I believe it would still have a hexagonal base. You can see here snowflakes grow from hexagonal prism. That's how they're all formed and based off of. And this is called snowflake branching, and the vapor falls over here and then freezes into a solid and makes the pretty little lacy type parts that are snowflake. And microgravity, all the vapor will be moving around in a different way, so that would make, I believe, a different formation. Now, why is this so important besides just being kind of cool? I believe that studying the snowflake formation could bring insight to bigger processes in the cosmos, such as galaxy formation, because they are similar processes in that snowflakes grow around a tiny fragment in the atmosphere, and they grow outward, like that, different layers. And galaxies grow in the same way, in that each layer of a galaxy growing out has a different chemical composition of the stars. So we could learn a lot about galaxy formation by studying snowflake formation. Also, more specifically, on Saturn, on its north pole, here we go, whoa! There's a hexagon on Saturn's north pole, and that's a big cloud vortex up there, and nobody knows why there's a big hexagon on that planet. And so, as I mentioned, snowflakes have a hexagonal base. I don't think that's a coincidence, because there's a lot of evidence I've found that it could be related. Saturn's core is surrounded by mostly hydrogen and helium, and its rings are composed of mostly water ice. Snowflakes, which are ice crystals, form because of hydrogen bonds, resulting in their symmetrical hexagonal shape. And I don't think it's a coincidence, because there's a lot of evidence that shows that they can be related. And this hexagonal cloud, right here, is a better view, is frequently the warmest spot on the planet surface, and snowflakes under warmer conditions are less intricate and more broad, like this big hexagon right here on the planet. And here's a snowflake that was grown under low supersaturation levels, and I think it looks pretty darn similar. And low supersaturation means that there's not a lot of water vapor surrounding the crystal as it's formed. So, besides just this one example, all that's learned from the far expanses of space can be applied to almost anything we can imagine creatively, or learning about different things on Earth or out in space, or anywhere we can imagine. And to expand our understanding of the universe really gives deeper meaning to everything else and how it all connects. And I was debating whether I should mention it or not, but I think I'm going to, because it really has a good message. I had the opportunity to speak at the North Middle School over there down the road to the 8th graders about, how to do well in school, and, tell them about my experiment and great stuff like that. And I thought back to what I could say to them, thinking back to middle school, and it made me realize that there was a kind of a turning point that allowed these really great chain of events to be here at Wheaton College and get the opportunity to be in the Space Lab contest. That in middle school I took an advanced math course, and that made me have extra credits when I changed for high school. And having those extra credits allowed me to get a few more credits easily during the summer, taking some courses, and that allowed me to be at Wheaton College earlier. And I've always really liked space. And I get to take the wonderful courses here with Professor Barker and Gary. And I was Gary. And I was exposed to all these great space things and research, and really sparked my interest, and that allowed me to do the experiment I did when I found out about the Space Lab. So the message I'm finally getting to is that doing your best wherever you are can really lead to opportunities that you'll be prepared for later on. And Dean put it well yesterday during rehearsal that if you tell a kid, do your math homework, you'll get to go to Mars and be an astronaut, that'll pretty much motivate them. So finally, I'd like to also take this time to thank Wheaton College for being so supportive of my experiment, and thank you all for listening.